What is Varactor Diode, Varicap Diode, and its working principles? A Varactor diode, also known as a Varicap diode or tuning diode, is a type of semiconductor diode designed to exploit the variable capacitance property of its p-n junction when reverse biased. Varactor diodes are used in electronic circuits for voltage-controlled tuning, frequency modulation, and voltage variable capacitance applications. The primary characteristic that sets Varactor diodes apart from standard diodes is their ability to vary their capacitance with applied voltage. When a reverse bias voltage is applied to the Varactor diode, the width of the depletion region, the region without charge carriers, at the p-n junction increases, resulting in a change in capacitance. The reverse bias voltage directly affects the width of the depletion region and, consequently, the capacitance. Key features and applications of Varactor diodes include: voltage-controlled capacitance refers to the property of certain electronic devices, particularly Varactor diodes, where the capacitance can be modulated or controlled by applying an external voltage. This phenomenon is utilized in various applications, especially in radio frequency, RF, and microwave circuits, to achieve voltage-tunable or voltage-variable capacitance. In a voltage-controlled capacitance device, such as a Varactor diode, the capacitance between two conductive elements, such as metal plates or semiconductor layers, changes in response to changes in the applied voltage. This effect is typically achieved by exploiting the variation of the depletion region's width in a p-n junction diode or a similar structure when a voltage is applied. Here's how voltage-controlled capacitance works in a Varactor diode. Depletion region and capacitance. In a reverse-biased p-n junction diode, like a Varactor diode, the electric field creates a depletion region devoid of free charge carriers. This depletion region acts as a dielectric insulator between the p-type and n-type regions of the diode. Capacitance variation. When a reverse bias voltage is applied to the diode, the width of the depletion region increases. The width of the depletion region determines the separation between the charged layers, which in turn affects the capacitance of the diode. A wider depletion region corresponds to a lower capacitance, and a narrower depletion region corresponds to a higher capacitance. Voltage control. By varying the reverse bias voltage across the diode, the width of the depletion region and thus the capacitance can be changed. Higher reverse bias voltages lead to a narrower depletion region and higher capacitance, while lower voltages result in a wider depletion region and lower capacitance. Applications of voltage-controlled capacitance include: frequency tuning. Voltage-controlled capacitance is used in Varactor diodes for frequency tuning in oscillators, filters, and other RF circuits. By varying the capacitance, the resonant frequency of the circuit can be tuned over a specific range. Phase-lock loops. PLL's voltage-controlled capacitance is used in PLL circuits to adjust the frequency of the local oscillator and achieve precise frequency synthesis. Voltage-controlled oscillators, VCOs. VCOs use voltage-controlled capacitance to adjust the output frequency based on the applied voltage, making them essential in RF communication systems. Frequency modulation. FM voltage-controlled capacitance is used in FM modulation circuits, where the capacitance is modulated by an input voltage, causing the output frequency to change accordingly. Voltage-controlled capacitance is a powerful tool in RF and microwave circuit design, enabling dynamic control over circuit parameters for applications like frequency tuning, modulation, and voltage variable filtering. It plays a critical role in modern communication systems, allowing engineers to achieve precise and flexible control over the behavior of electronic devices. Frequency tuning refers to the process of adjusting the frequency of an electronic circuit, device, or system to a desired value. It is a crucial operation in various applications, particularly in communication systems, where precise control over frequency is essential for proper signal transmission, reception, and modulation. Frequency tuning allows for optimizing performance, avoiding interference, and adapting to changing conditions. Frequency tuning can be achieved through different methods, depending on the specific application and requirements. Some common techniques for frequency tuning include: Varactor diodes. Varactor diodes are used for voltage-controlled frequency tuning in RF and microwave circuits. By changing the applied voltage to a Varactor diode, its capacitance changes, affecting the resonant frequency of the circuit. Voltage-controlled oscillators, VCOs are circuits that generate output signals with frequencies that can be tuned by varying an input voltage. They are commonly used in communication systems to provide tunable carrier frequencies for transmission and reception. Phase-locked loops, PLLs are feedback control systems that compare the phase and frequency of a reference signal with a feedback signal. They can be used for precise frequency synthesis, tracking, and tuning in various applications. Frequency synthesizers generate output frequencies that are multiples of a reference frequency. They are used to generate specific frequencies required for various communication standards and protocols. Mechanical tuning elements. In some applications, mechanical components such as variable capacitors or inductors can be physically adjusted to change the resonant frequency of a circuit. This method is less common in modern electronics due to its mechanical complexity. Digital frequency synthesis involves generating frequencies using digital techniques such as frequency division, multiplication, and phase accumulation. This approach is commonly used in digital signal processing and modern communication systems. Frequency tuning is essential in various industries and applications. In wireless communication systems, frequency tuning ensures that transmitters and receivers are operating on the correct frequency bands to prevent interference and ensure efficient signal transmission and reception. In radio and television broadcasting, frequency tuning is used to select different channels for broadcasting and reception. In radar systems, frequency tuning allows radar operators to adjust the radar's operating frequency based on the target characteristics and environmental conditions. In scientific instruments and research equipment, frequency tuning is used to precisely control the frequency of electromagnetic waves in experiments and measurements. Overall, frequency tuning is a critical aspect of electronic systems that require precise control over frequency parameters. It enables the optimization of performance, adaptability to different conditions, and effective communication in various technological applications. Frequency modulation, FM, is a modulation technique used in communication systems to transmit information by varying the frequency of a carrier signal in response to the changes in the amplitude of a modulating signal. In FM, the frequency of the carrier wave is modulated while the amplitude remains constant. FM is widely used in broadcasting, two-way radio communication, radar systems, and various other applications. Key characteristics and concepts of frequency modulation, FM, include 1. Modulating signal. The modulating signal is the input signal that carries the information to be transmitted. It could be an audio signal, voice or music, or data signal, digital information. The amplitude of the modulating signal varies, and this variation is translated into changes in the frequency of the carrier signal. 2. Carrier signal. The carrier signal is a high-frequency sinusoidal waveform that is modulated to transmit the information. The frequency of the carrier signal is the frequency around which the variation occurs. 3. Frequency deviation. The maximum amount by which the carrier frequency is allowed to deviate from its center frequency is called the frequency deviation. It is directly proportional to the amplitude of the modulating signal and determines the extent of frequency variation. For frequency deviation sensitivity, this is the ratio of the change in frequency deviation to the change in amplitude of the modulating signal. It determines how much the frequency changes for a given change in the modulating signal's amplitude. 5. Modulation index. The modulation index, M, represents the ratio of the frequency deviation to the frequency of the modulating signal. It indicates the degree of modulation and affects the frequency variation. 6. Demodulation. Demodulation is the process of extracting the original modulating signal from a modulated carrier signal. In FM, this involves recovering the original audio or data signal from the frequency-modulated carrier signal. 7. Advantages of FM. FM is less susceptible to amplitude variations due to noise, making it more resilient in noisy environments compared to amplitude modulation, AM. FM offers better audio quality and fidelity, making it suitable for high-quality sound transmission in broadcasting. FM is less affected by electromagnetic interference and fading effects compared to AM. 8. Applications of FM. FM broadcasting. Many radio stations use FM to transmit audio signals with high-quality sound. Two-way radio communication. FM is used in walkie-talkies, mobile radios, and other communication devices. Radar systems. FM radar systems are used for target detection, distance measurement, and speed determination. Television sound transmission. FM is used for transmitting audio signals in television broadcasts. In FM, the frequency variations of the carrier signal are directly related to the instantaneous amplitude of the modulating signal. As a result, FM offers advantages in terms of noise immunity and audio quality, making it a preferred choice for applications that require high-fidelity audio transmission and robust communication in various environments. Voltage-controlled oscillators, VCOs. A voltage-controlled oscillator, VCO, is an electronic oscillator whose output frequency can be controlled by an external voltage signal. VCOs are fundamental components in communication systems, electronic instruments, and various applications where precise frequency tuning and modulation are required. They are commonly used in frequency synthesizers, phase-locked loops, PLLs, and signal generators. Key characteristics and concepts of voltage-controlled oscillators, VCOs, include 1. Frequency tuning. The primary feature of a VCO is its ability to produce an output signal with a frequency that can be varied by changing an input voltage. By adjusting the input voltage, the VCO's output frequency can be tuned over a specific frequency range. 2. Oscillation range. The range of frequencies over which a VCO can operate is referred to as its oscillation range. This range is determined by the VCO's design and the properties of the components used. 3. Tuning sensitivity. Tuning sensitivity refers to the rate of change of the VCO's output frequency with respect to changes in the input control voltage. It indicates how much the frequency changes for a given change in voltage. 4. Modulation. VCOs are commonly used for frequency modulation, FM, applications. By applying an input modulation signal, such as an audio signal, the VCO's output frequency is modulated, resulting in a frequency-modulated signal. 5. Applications of VCOs. Frequency synthesis. VCOs are used in frequency synthesizers to generate stable and precise frequencies required for communication systems, such as in radio transceivers. Phase-locked loops, PLLs. VCOs are often part of PLL circuits used for frequency multiplication, frequency translation, and clock synchronization. Signal generators. VCOs are used in signal generators to produce continuous wave signals with variable frequencies for testing and calibration purposes. Frequency modulation. VCOs are used to generate frequency-modulated signals in FM radio broadcasting, wireless communication, and radar systems. Voltage-to-frequency conversion. VCOs are used in applications where an input voltage needs to be converted into a frequency output, such as in sensor interfaces. 6. Types of VCOs. LC oscillators. VCOs based on inductor capacitor (LC) resonance circuits are commonly used in RF applications. Ring oscillators. Ring oscillators consist of an odd number of inverters connected in a ring. They are simple and often used in integrated circuits. Voltage-tune oscillators. These VCOs use a Varactor diode to vary the capacitance and, consequently, the oscillation frequency with an applied voltage. 7. Design considerations. Designing VCOs involves considerations such as stability, phase noise, tuning range, power consumption, and output waveform purity. Voltage-controlled oscillators are versatile and essential components in various electronic systems. Their ability to generate frequency-tunable signals makes them valuable for applications ranging from wireless communication to test and measurement equipment. Voltage-controlled filters, VCFs, are electronic circuits that allow the characteristics of a filter, such as cutoff frequency, resonance, and bandwidth, to be controlled or modulated by an external voltage signal. These filters are used in various audio and signal processing applications to shape and modify the frequency content of signals based on voltage inputs. VCFs are commonly used in synthesizers, audio effects processors, and other electronic music equipment to create dynamic and expressive sound effects. They provide a way to manipulate the timbre and tonal qualities of audio signals in real time. Key features and concepts of voltage-controlled filters include: 1. Filter types. Voltage-controlled filters can be designed using various types of filter configurations, such as low-pass, high-pass, band-pass, and notch filters. Each type of filter affects the frequency content of a signal differently. 2. Cutoff frequency control. The most common parameter controlled by voltage in VCFs is the cutoff frequency. The cutoff frequency determines the point at which a filter starts attenuating frequencies. By adjusting the control voltage, the cutoff frequency can be shifted, allowing different frequency ranges to pass through the filter. 3. Resonance control. Many VCFs also provide resonance control, which emphasizes frequencies near the cutoff point. Resonance can be adjusted using a voltage input to create a characteristic peak in the filter's frequency response. 4. Bandwidth control. For certain filter types, such as band pass and notch filters, the bandwidth can be controlled by voltage. This allows you to adjust the width of the frequency band that the filter affects. 5. Modulation sources. The control voltage for a VCF can come from various sources, including envelopes, LFOs, low-frequency oscillators, sequencers, and other modulation generators. This allows for dynamic and evolving changes to the filter's behavior. 6. Voltage to frequency conversion. Some VCFs can convert control voltage to frequency, creating unique and expressive modulation effects. As the control voltage changes, the filter's behavior shifts in response. 7. Applications. Voltage-controlled filters are used in electronic music production and sound synthesis to shape sounds in real time. They can create effects such as sweeping filter sweeps, resonant sweeps, and evolving textures. 8. Filter orders. VCFs can be designed as different orders, such as first order, second order, etc., affecting the steepness of the filter's roll-off and the slope of its frequency response. Voltage-controlled filters are a powerful tool for sound designers and musicians to manipulate audio signals in creative and expressive ways. They are integral to modular synthesizers and other electronic music setups, allowing for real-time manipulation of sound textures and sonic characteristics. Modulation circuits. Modulation circuits are electronic circuits used to apply modulation techniques to a carrier signal, resulting in the transfer of information from a modulating signal to the carrier signal. Modulation is a fundamental concept in communication systems, enabling the transmission of data, voice, and other information over various mediums. Different modulation techniques alter different properties of the carrier signal, such as amplitude, frequency, or phase, to encode the information from the modulating signal. Modulation circuits are critical components in various communication systems, including radio broadcasting, television transmission, wireless communication, and more. Here are some common types of modulation circuits and their applications. 1. Amplitude modulation, AM, circuits. Amplitude modulation involves varying the amplitude of the carrier signal in proportion to the amplitude of the modulating signal. AM circuits include amplitude modulators. These circuits combine the carrier signal with the modulating signal to produce an amplitude-modulated signal. AM is widely used in AM radio broadcasting. 2. Frequency modulation, FM, circuits. Frequency modulation involves varying the frequency of the carrier signal based on the amplitude of the modulating signal. FM circuits include frequency modulators. These circuits change the frequency of the carrier signal according to the modulating signal's amplitude. FM is commonly used in FM radio broadcasting and many wireless communication systems. 3. Phase modulation, PM, circuits. Phase modulation involves changing the phase of the carrier signal in response to the modulating signal. PM circuits include phase modulators. These circuits alter the phase of the carrier signal based on the modulating signal's amplitude. PM is used in various communication systems, including digital modulation schemes. 4. Quadrature modulation circuits. Quadrature modulation techniques, such as quadrature amplitude modulation, QAM, and quadrature phase shift keying, QPSK, combine both amplitude and phase modulation. Quadrature modulation circuits include QAM and QPSK modulators. These circuits generate signals with combinations of amplitude and phase variations, allowing higher data rates and more efficient use of bandwidth. 5. Pulse modulation circuits. Pulse modulation involves encoding information in the form of pulses, and it includes techniques like pulse amplitude modulation, PAM, pulse width modulation, PWM, and pulse position modulation, PPM. Pulse modulation circuits include pulse modulators. These circuits shape the carrier signal's pulses based on the modulating signal, encoding the information in pulse characteristics. Modulation circuits are crucial for transmitting information effectively and efficiently over various communication channels. They play a central role in the design and operation of communication systems by allowing information to be encoded onto carrier signals and then decoded at the receiving end using appropriate demodulation circuits. Voltage-controlled voltage sources, VCVS, are electronic circuits that generate an output voltage that is controlled by an input voltage signal. These circuits are used in various applications where a variable voltage needs to be generated based on an external control voltage. VCVS is a fundamental building block in electronics and is used in a wide range of analog and mixed signal circuits. In a VCVS, the output voltage is proportional to the input control voltage, and this proportionality is defined by the circuit's gain or transfer function. The control voltage can come from various sources, such as sensors, feedback loops, or other electronic circuits. Key features and concepts of voltage-controlled voltage sources include 1. Gain. The gain of a VCVS determines the ratio of the output voltage to the input control voltage. It represents how much the output voltage changes for a given change in the input voltage. 2. Linear and nonlinear responses. In some cases, the output of a VCVS might have a linear relationship with the control voltage, while in others, it might exhibit nonlinear behavior based on the specific circuit design. 3. Applications of VCVS. Amplifiers. VCVS circuits are used in amplifier designs, where the gain can be controlled by an input control voltage. Automatic gain control, AGC. In communication systems, AGC circuits use VCVS to maintain a consistent output level despite varying input signal strengths. Temperature compensation. VCVS circuits can be used in temperature compensation circuits to adjust voltages based on temperature changes. Feedback loops. VCVS circuits are commonly used in feedback loops to control amplification, filtering, and other circuit characteristics. Voltage scaling. VCVS circuits can be used to scale voltages up or down based on control voltages, which is useful in various signal processing applications. 4. Examples of VCVS. Operational amplifiers. Op-amps can be configured as VCVS by connecting their inverting or non-inverting inputs to the control voltage source and using appropriate feedback elements. Multiplier circuits. Some specialized circuits are designed to perform voltage multiplication based on control voltages. Voltage-controlled oscillators. VCOs generate output voltages that vary based on control voltages, making them a type of VCVS. 5. Linear and nonlinear applications. VCVS can be used in both linear and nonlinear applications. In linear applications, VCVS is used to provide controlled amplification or attenuation of signals. In nonlinear applications, VCVS is used for functions like modulation, signal processing, and control systems. Voltage-controlled voltage sources are versatile and important components in electronics. They enable designers to create circuits that respond dynamically to changing conditions or input signals, making them essential in various applications that require voltage control and modulation. Varactor diodes are available in various semiconductor materials, such as silicon and gallium arsenide, and their characteristics can be optimized for specific applications by choosing appropriate materials and designs. The ability to control capacitance with an applied voltage makes Varactor diodes versatile components in RF and microwave systems, enabling precise frequency control and modulation in various electronic circuits.